2f1fa19c3m1b7c8e13c9c6d3p38d19d7b9h. I just realized this doesn't have the little keynotes here, and I don't know what I did with them. So we're talking about how to split fermions. This is probably, I think this is video number 2. So line 22f1fa19c3m1b7c8e13c9c6d3p38d19d7b9h. Quarks break free fermion split 5G Wow Seti. There's the alien radio signal. March 17, 2013. Today's April 21st. So how to split a fermion in 2 previous video. There's a line of data from Waals force molecular 5G Wow Seti. The keyword is split intramolecular attractions. Quotes and diagrams are from Wiki. So it shows the symbols for hydrogen, carbon, water, ethylene, acetylene. Examples of Lewis dot style chemical bonds between carbon C, hydrogen H, and oxygen O. Lewis dot pictures represent an early attempt to describe chemical bonding and are still widely used today. My thoughts. What are the chemical bonds in a quark? Quote diagrams from blog. Quarks break free at 2 trillion degrees, June 23, 2011. So this is RHIC tunable energy range, quark gluon plasma phase, and it shows a baryon chemical potential and temperature scale. That's the latest QCD phase diagram. Physicists in the US, India, this is a quote, and China have calculated that quarks and gluons can break free from their confinement inside protons and neutrons at a temperature of around 2 trillion degrees Kelvin. The temperature of the universe a fraction of a second after the Big Bang. The researchers arrived at this figure by combining the results of supercomputer calculations and heavy ion collision experiments. They say that it puts our knowledge of quark matter on a firmer footing. According to the Big Bang model, the very early universe was filled with quark gluon plasma in which quarks and gluons, the carriers of the strong nuclear force, existed as individual entities. The strong force between quarks increases rapidly with distance, which means that the quarks need large amounts of energy to remain free, and therefore the plasma can only exist at extremely high temperatures. When the cosmos was only about a millionth of a second old, it had cooled to the point where quarks and gluons combined to form composite particles such as protons and neutrons. Exactly what this temperature is, however, has not been easy to work out. The theory of quantum chromodynamics explains the interactions of quarks and gluons extremely well, at very small distances, which are relevant to the collisions taking place inside the Large Hadron Collider LHC at CERN in Geneva. But at the larger distances characteristics of the quark-gluon plasma, QCD fails because it becomes impossible to account for all of the constituent interactions, which include many virtual pairs of quarks and antiquarks. So physicists use an approximation of the theory known as lattice QCD. So there's another keyword, lattice again, in which the complexity of quark-gluon interaction is limited by breaking down space-time into manageable chunks. Anchoring lattice QCD, now new XU of the XU, I don't know how to say that. I'm guessing it's XU, so it's XU, I don't know. Of the Central China, sorry if I got it wrong, Central China Normal University and the Lawrence Berkeley National Laboratory in California. And colleagues have anchored the value. Oh boy, sorry. Maybe I shouldn't do this first thing in the morning. I'm half asleep. It's the only time it's quiet enough. Have anchored the value of one of the key parameters of lattice QCD. They use results from the star detector at Brookhaven's laboratory relativistic heavy ion collider. I didn't know about that one. I should have got pictures of that. Which collides gold ions together at high energies to work out the temperature at which the quark gluon plasma condenses to form individual hadrons. Team member Badangas Mohanty of the Variable Energy Cyclotron Center in Kolkata, India, explains that knowing this temperature helps to map out the phase diagram of QCD. This diagram charts the transition from normal hadronic matter to quark matter, or possibly to another exotic state known as color superconductivity, as 2 variables are altered. These are the temperature and baryonic chemical potential, the latter being the energy needed to remove or add a proton or neutron to the strongly interacting matter. He points out that thermodynamics can be used to work out how the temperature of water's phase transitions varies with pressure, but that absolute values for these temperatures require the measurement of at least one fixed point within the phase diagram. Say the boiling point at atmospheric pressure. Likewise, he says, in QCD we want to find out what is the temperature of the phase transition at zero chemical potential. Calculating susceptibilities. Zhu and co-workers didn't measure this temperature directly, but derived it from theory and experiment. On the theoretical side, Surendu Gupta and others at the Tata Institute of Fundamental Research in India calculated the first, second, third, and fourth derivatives of the baryonic chemical potential with respect to pressure, and then worked out these susceptibilities should vary with temperature. Meanwhile, the experimental half of the collaboration counted how many more protons than antiprotons were produced in millions of collisions of gold ions at RHIC and plotted the variation in this measured quantity. At the quark-gluon plasma transition temperature, certain combinations of the theoretical susceptibilities should numerically equal particular quantities relating to the shape and the measured distributions. So by varying the susceptibilities with temperature until they equaled the quantities derived from experiment, the researchers arrived at a value for the transition temperature. The value obtained by Zhu's team was 175 plus 1 divided by minus 7 MeV, equivalent to the 2 times 10 to the power of 12 Kelvin, which is exactly the value predicted by other indirect methods in lattice QCD. This is the first time there has been a direct comparison between high temperature and quark matter theory and high energy experiments, says Mohanty. People have predicted that the theoretical susceptibilities should be, but you need to compare these predictions with the experiment to be sure that the theory is correct. Finding a critical point. The next steps, adds Mohanty, is to measure a predicted critical point within the QCD phase diagram. At a critical point, a boundary between two phases comes to an end and the properties of the two phases become identical. There is a critical point for liquid water and steam. Now that's another keyword there. Liquid water and steam, that's something we're using in the communication signal. So that was interesting. So for example, the nuclear physicists believe that likewise there is one for more normal and quark matter. Finding this critical point will involve carrying out heavy ion collisions over a range of collision energies, something, says Mohanty, which RIC is ideally suited to. I don't agree with you guys. I think if you mixed it with some sort of super alloy or something that can raise the temperature and spike it quick enough, you might actually get some better results. The LHCs, that's just a thought that came to mind. I don't know if it'll work or not, but there's something for you. The LHC's Alice detector, on the other hand, should be able to nail down the quark-gluon plasma's viscosity, with previous measurements having suggested that the plasma has a lower viscosity than any other liquid in the universe. David Evans, a physicist at Birmingham, you know what? I don't know if that idea will work, but I'm going to look it up and see if it does. Okay, so we need to find a superalloy spikes temperature of quarks, right? You guys need something that just so you can measure whatever it is you're measuring. Suggested that the plasma is a lower viscosity than any other liquid in the universe. Oh, liquid water. We were talking about liquid water and what else? And steam. Now steam is hot, so that would spike it up too by adding steam to the superalloy, and maybe that sets off some sort of chemical reaction. That might help. Okay, so the LHC's Alice detector, on the other hand, should be able to nail down the quark-gluon plasma's viscosity. And let's put Alice down there. Suggests that the plasma has a lower viscosity than any other liquid in the universe. David Evans, a physicist at Birmingham University, the head of the UK group at Alice, is impressed by the latest work. I think these techniques will allow theorists to tune up and improve lattice QCD by direct comparisons with experiment, he says, and hence provide even better calculation predictions in the future. However, Johann Rafalski of the University of Arizona believes that the research suffers from major deficiencies, in particular lack of analysis of systematic errors. For example, he says, you and colleagues have not accounted for the fact that the detector counts only a limited fraction of all collision products. The total systematic error is very probably much larger than the statistical error as presented. He says, adding that his colleagues from the lattice QCD community believe that this analysis has errors at every step. Something about lattice QCD. The research is published, but the author Edwin Cartlidge is a science writer based in Rome. Physicsworld.com. So cool, that's from Rome. Keyword ideas: split supersymmetry. The keywords baryons or fermions, while the mesons are bosons. Hyperphysics.phy-astr.gsu.edu. Keyword: how to split a fermion in 3 will be in the next video. Just realize that this is the research for it, and then of course there's going to be a formula to put together to see. Well, you can try it out and see if it splits a fermion or not. My guess is it will. Thanks for watching.